Hi, I'm Professor Tim Townsend with the University of Florida, Department of Environmental Engineering Sciences. This presentation is one that we gave for a Hinkley Center for Solid and Hazardous Waste Management project, the project being characterization and management of per and polyfluorinated alkyl substances, PFAS, remediation residuals. This was presented as our second TAG meeting, Technical Awareness Group meeting. Our TAG was a group of professionals who participated in early meetings about what we were doing on the project and provided us some feedback. This is the part of the project where we're about to wrap up, presenting to the TAG and getting ready to submit a draft final report for review. Look forward to hearing any potential comments you might have, and thank you for listening. Go over some background. I'm going to have Jake talk a little bit. The goal was not to give a tremendous background on PFAS because I think most people know about that, and then share a little bit about some of these risk-based thresholds that are out there, either provisional through the state of Florida or more recently from the US EPA. Talk a little bit about EPA roadmap and some of the efforts going on there and how it feeds into what we're talking about. And then there are two big projects that we're going to talk about. And then I'll mention more about that in a second. Then we'll have plenty of time to have discussion at the end. Next slide, please, Jake. Okay. And just real quick, so the Hinkley Center, has funded work on PFAS before. There's several other ongoing projects. This is Helena's original project about PFAS releases from landfills in Florida. There's information out there, including report and paper. And then we have the big EPA project that we're doing right now. And so there's been a large effort on PFAS. And again, we're not here to talk all about that today. A number of the folks on the call here today, Brian and Leo, are contract managers for this large thermal treatment project, which was kicked off at the beginning of this year, which will be conducted over the next 2 years or so. Next slide, Jake. So I was going to turn it over to you, Jake, say a little bit about some background, then I'll jump back in a minute.
Okay. Yeah. So I'm just going to give some quick background on PFAS because I'm sure all of you guys are pretty much experts on this stuff at this point. So PFAS are just a group of over 4,000 compounds, and they're ubiquitous in a lot of industrial and consumer products. PFAS have been shown to be toxic, they're mobile in the environment, and they're extremely resistant to biodegradation. So this combination of effects has kind of sparked remediation or regulatory agencies to start developing standards to limit the exposure to PFAS. And originally, focus was developed on drinking water standards, but more recently, there have been soil-based limits for PFAS. Oh, I think I missed a slide. Sorry. Oh, I'm sorry. There's a technical difficulty here. I lost a slide. I'll just share and just talk about what it would have been. Sorry. Yeah. So basically, there have been, regulations, as I mentioned. These regulations are both for direct exposure and for leachability. And we're fortunate enough, to have people on the call who actually developed the leachability and direct exposure limits for the state of Florida FDUP's provisional soil cleanup target levels. And this kind of leads into, with all these new regulations being developed, both at the federal and the state level, there's this push to start remediating contaminated soil. So, with remediation comes, the waste management. What do you do with contaminated soil? EPA has provided some guidance over this, but it comes with some caveats. So, managing it, you can still put it in a traditional subtitle, de-landfill. PFAS are not hazardous waste. But, as Dr. Solo's, previous Hinkley Center work showed that PFAS do show up in landfill leachate, suggesting, that they're mobile. So if you put, contaminated soil or remediation byproducts in a landfill, you could get migration out over time. And then there's another option, which would be thermal destruction, but, this is still kind of in the research phase. It's not really done at the commercial scale yet. So as researchers, the development of these new regulations and then also the creation of these remediation ways leads to some really important questions that need answers. So kind of first, it's like, how do risk-based leachability thresholds compare to real leaching data, of contaminated soils? And then how do you best manage these PFAS containing waste so that way the PFAS are either contained or destroyed? And I'm going to pass it over to Dr. Townsend to kind of explain how we plan to answer that second question.
Yeah, so let me back up a second. So that slide we were going to show that didn't show a couple things in it. First of all, Brian's office, Department of Environmental Protection, they maintain a set of what we'll call soil cleanup target levels for different chemicals, pollutants that we might encounter in soils as part of a remediation project, but like over in Kim's group, when they start talking about beneficial use. So we have these risk-based, we'll call screening levels or soil cleanup target levels. And DEP is maintained for several years now, again, thanks to Leah Stuckel and her group, some provisional soil cleanup target levels, both from a direct exposure perspective and from a leachability perspective. Part of what we're going to talk about today, it's just important to bring that up. I think we have slides later that give that a little bit more background on that. What we wanted to show in that slide is that just, I think that FABIT Dr. Tolomat last week forwarded on to us anyway, is that at the EPA level, they maintain what's known as regional screening levels, which are somewhat of a federal version of soil cleanup target level. They're not regulations, they're not standards, but they're risk-based screening levels. And they recently released for, was it 5 or 6, Jake?
6.
6 PFAS compounds, their new regional screening levels. And so that was something that's a little bit new to us in terms of that info. So we've incorporated some of that information in there. Now, the 2 questions that we're going to address today, number one is that for these risk-based soil cleanup target levels, provisional based on leachability, how protective are they? This is a conversation I've had with Brian and Leah before, but the idea is that, as we'll go into, they are mathematically derived depending on some assumptions regarding how PFAS will partition into soils. We'll illustrate that a little bit more. So one question that this Hinkley Center project is trying to resolve is whether or not the current soil cleanup target levels for leachability, how well do they compare if you actually do a leach test? And I'll illustrate that more a little bit in a second. The second real question then is, originally this project was going to involve doing some laboratory scale thermal treatment. Because of COVID and conditions at the university and repairs and infrastructure improvements, that was kind of switched over to evaluate what about the disposal of liquid waste going into landfills that might have PFAS. And a common practice, and one reason why we have Jim on the call with us, is that there are facilities that will do bulking and will take liquid waste, bulk them up. And as long as they're not a hazardous waste, which PFAS currently is not under RCRA, then those can be disposed of in a Subtitle D landfill or a Class 1 landfill. So anyway, I apologize for rambling on this one slide, but we'll try to hit some of those things. But it was important just to acknowledge that recently EPA has come out with more guidance that folks who are dealing with contaminated media and PFAS could potentially use. Go ahead, what's that next slide, Jake? Mm-hmm. Yeah, so I'll hand this back to you in a second. But so this first question that we're posing here, how do these risk-based leachability thresholds compare to laboratory leaching data on contaminated soils, particularly AFFF contaminated soils? I think you have one slide here, right, Jake?
Yep. Yeah. So just kind of to reiterate everything, there's EPA soil cleanup target levels, and there's FDEP soil cleanup target levels. These are both relatively new, but there's also, it's important to distinguish that there's levels that are based on direct exposure. So, ingesting contaminated media, coming in contact with your skin or breathing in the dust. but then there's also another pathway that that regulators account for risk management, and that's leachability into groundwater. And something that's important to really highlight is that the levels for direct exposure are much higher than the levels for leachability-based risk. So you can see for the FDEP for PFOA, it's 100 times, 1,000 times greater, roughly for the risk for direct exposure versus leachability. And the same thing is true for these new regional screening levels that were developed or just released by EPA. So now I'm going to pass it back to Dr. Townsend to kind of explain how these leachability-based risk thresholds are developed.
So again, when you we're kind of in the awkward position of we're presenting this material to the people who've developed, maintain these programs. But the idea is that as an environmental engineer, particularly as a solid waste engineer, when we want to, for example, look at whether a contaminated soil or a waste product is going to pose a risk, we look at these two pathways, the direct exposure pathway and the leaching to groundwater pathway. And DEP has provisional soil cleanup target levels for both. But as Jake just pointed out, the one that is the lowest by far is the protection of groundwater, the leachability-based soil cleanup target level, suggesting that if contamination of groundwater is a concern in a particular project, then that is going to be the most limiting threshold that you're going to have to deal with. And then the same thing for these new RSLs. It's the leachability number, which is much lower than the direct exposure, in this case, soil screening level. And in fact, those numbers are also a little bit lower than the Florida soil cleanup target level. So anyway, I went back and we've been dealing with this for a couple decades. There's a product in Florida called RSM, or recovered screen material, which is produced from C&D recycling facilities. That you might remember a little bit about that. But the idea is that back in this was even in the late 90s, this whole issue of, do you do a leach test or can you use the actual soil cleanup target level for leaching, which is a mathematical calculation? Is that an appropriate? If you do a leach test, it's just more work, it's more cost. So if you can just do a totals measurement and compare it to the soil cleanup target level based on leaching, then you would certainly rather do that. So I tried to put these slides together just to get us on the same page. So just consider, for example, a typical soil aquifer system. And then of course we have a groundwater monitoring well at some point, which will make a little bit more sense here in the next slide. Next, Jake. Mm-hmm. So imagine that we had a spill, or it could have been just intentional use of AFFF at an airport or a fire training college, and it gets onto the soil. And now this soil has PFAS compounds in there. One of the things you would do, next slide, is you would, of course, go collect a sample of soil. You would send that off to the laboratory, and you then would potentially do one of several tests. One test is you just look for the total concentration in milligram per kilogram of the PFAS chemicals which are in that soil. What that allows you to do is not only assess that direct exposure risk, because there are soil cleanup target levels developed for direct exposure. They're provisional in Florida for the PFOA and PFOS. But there are also provisional soil cleanup target levels for protection of groundwater in Florida that you could also look at. And again, those are lower than the direct exposure ones. Alternatively, we could also take that soil and we could do a leaching test. And then we can actually measure what is the concentration in the leachate that's produced when the soil contacts water. And one would argue that that probably is a more accurate way of trying to see the potential leaching mobility or risk to groundwater. But it's a second test. And so the idea is that if we can use the total concentrations and compare that, why do we even, or do we even need to do the leach test? So next slide, please. So the idea is that, okay, how do you even come up with a soil cleanup target level based on leachability? So it's almost like doing a mathematical leach test, okay, the way they derive these things. So just imagine we have this environment in our soil where there's, of course, in addition to the soil particles, the solids themselves, there's water in there. And then, of course, if it's unsaturated, there's going to be air in there as well, or a vapor phase. And just schematically have tried to indicate here that a red dot would indicate, for example, PFAS. If you could, next slide, please, Jay. The idea is that some of the PFAS will sorb to the soil, and particularly for organic chemicals, it's a function of the organic matter. They sorb to the organic matter, but some of it will dissolve into the water. And so there's this equilibrium that is reached between the PFAS on the soil and the PFAS in the water. Now, when you collect a sample, however, and you send it to a lab, you're measuring kind of all of that. Next slide, please, Jake. And so the idea is that this term that relates the amount that will be in the water versus the amount that will be on the soil itself is called a partition coefficient, or K sub D. And it's actually for organic chemicals, we typically calculate this depending on the organic content of the soil, but I'm just simplifying it here and calling it the partition coefficient, which is really like the octanol water coefficient times the fraction of organic matter. But bottom line, though, is that when someone develops a leachability-based risk-based screening level, like a soil cleanup target level, what they're doing is they're having to take some data and assuming, well, what is the partition coefficient? What is the amount of water that's in the soil? And what the soil cleanup target level is for leaching is it's basically what soil concentration would you have to be at so that below that number, the leachate which would result from it would be less than the groundwater cleanup target level. Okay, let's go to the next slide quick. So this is the equation in simplified form. And so if you go to the documents that are on the DEP website or dig into even the EPA regional screening levels, your soil cleanup target level for protection of groundwater is basically the groundwater cleanup target level. Now, Florida includes a dilution factor in this case. And then there's this term of the partition coefficient with the volumetric water content over the density, which is really just a way to relate how much water is in that soil. Now, I have neglected in this case, because there's a whole nother term that has the gas phase and the Henry's law constant, things like that. But let's just think about the partitioning of the soil between water and the soil phase. So again, DEP, I mean, and with, UF and, Leah Stuckel's group and everything have helped develop these target levels that allow you to take a totals concentration and say, okay, this is the concentration that you need to be at to be protective of groundwater to meet a groundwater cleanup target level. But bottom line is that it's that KD value that really, that partition coefficient, that is what controls that number. Okay, next slide, please. And so again, just quick note, same approach used for the US EPA screening level. And so if you rearrange that equation, and hopefully it'll make sense why I'm going through this, is that if the concentration in the water phase should be the concentration in the soil phase divided by the partition coefficient plus the liquid to solid ratio. Okay. And so what this allows us to do then is to be able to compare. So where we're going with this project is we wanted to run leach tests on AFFF contaminated soil and see whether or not it leached above the provisional groundwater cleanup target level for PFOA or PFOS, and then take the total concentration and take that total concentration and see whether it would have exceeded the leachability-based soil screening level or soil cleanup target level. And what that would do is that would enable us to be able to say, yeah, the current provisional target levels are a pretty good estimate of what the leachability risk, or they overestimate leachability risk, or they underestimate leachability risk. And so the way we're going to present this data is something like this, is that you can actually, because when you do a leach test, of course, there's a lot more water than soil compared to what's actually in the soil itself, right? And so using this mathematical relationship based on the concentration that's in the soil, you can basically come up with what the predicted concentration in the liquid phase is a function of liquid to solid ratio. And so there's a test which Jake will talk about. It's one of the LEAF methods called method 1316, where we look at leachability as a function of liquid to solid ratio. And if we, so that line right there would be based on a given total concentration of PFOA or PFOS or whatever chemical of interest, as well as that KD value, which we talked about, okay? And so if it lies above that line, this is a quick way of graphically comparing the data. It suggests that maybe the screening level of the target level underestimates the amount of leaching that's predicted. If it's below the line, it's going to tend to overestimate it. So when Jake goes through this data in a minute, and he'll show this again to refresh your memory, it gives us a good way to see whether or not our mathematical leaching test, which is the soil cleanup target level for protection of groundwater, or the soil screening level for protection of groundwater, does a good job when compared to actual leaching tests. And so with that, Jake, I think you're going to turn that over and let him go through the methods and what was done and talk about the results, and then we can stop and go back and ask any questions that you want. And I guess just one real note for Brian, you know, on your side, and Leah, is that plot that we just showed, we're just taking that dilution factor out so we can really just factor in what the impact of that KD value is. Okay, go ahead, Jake.
All right, perfect. So as Dr. Townsend explained,
hey, Jake, 1 second. I think Thabit, you want to ask a question now? Sure, if you got one now, go for it.
Not at the moment, but I would rather to be able to understand it better.
Yeah.
Maybe it's a good idea to just ask the question. I will raise my hand if I have a question. But.
Yeah. Just the trick is just get our attention and we'll stop. Absolutely.
Yeah. Okay. Yeah. So as Dr. Townsend mentioned, you know, our goal is to compare the equations used to develop these risk-based thresholds to actual leaching data. So to get this actual leaching data, we need to, you know, find the total concentration of an AFFF contaminated soil and also run leaching tests on it. So like the first step of that is to get actual AFFF impacted soils. So what we did is we got 2 different soils. They were donated to us by Jim Clark, and we ran characterization on them. So part of that KD is a function of organic matter content. So we ran organic matter, ran moisture content, pH, and then our total PFAS. And then we also conducted different leaching tests. So we conducted method 1313, which is leaching as a function of pH, method 1316, which is the leaching as a function of liquid solid ratio. And that's what we'll actually compare our data to. If you remember Dr. Townsend's slide, the x-axis is liquid solid ratio. So that fits nicely with this leaching test. And then we also...
Thabit has a question. So
yeah.
Can you give us a little bit more about the background where the soil, it is contaminated soil. What is the source? Is it a...
Yeah.
Well, let me just say, I mean, this was provided to us by a facility that receives contaminated soils for ultimate bulking, treatment, and then disposal. And so, Jim, I don't know if you can remember exactly the what the source of these was or not. If you don't feel comfortable answering, don't feel the need to. Jim, did you hear me? Jim Clark? And you're on mute, by the way. Maybe Jake, you can unmute Jim.
Yeah, let's see if I can do that.
Jim, you're muted right now, so hold on a second.
You're gonna have to unmute yourself. I can't.
Okay, how about now?
Yep,
great,
perfect.
Okay, I believe one of the soils came from an airport where they had used AFFF and opened it up and had the tank where they opened and tested and all that. And the other one was from a dry cleaning program.
Good, thanks, Jim. That helped.
Yes.
Okay, perfect. Yeah, so we ran leaching tests on it, but we're just going to highlight the results of our method 1316, which is leaching as a function of liquid solid ratio. But there's also other leaching data that we'll include in our Hinkley Center report. So to give an idea of what these batch leaching tests look like, we take our contaminated soil and we'll add different amounts of liquid to it. So that's the liquid to solid ratio. And then we'll rotate it for a given amount of time.
And for the 1316, it's just deionized water.
Yes, yeah. So it's just DI water. And then we rotate in these big rotators, and then we'll centrifuge and extract out the liquid that comes off after contacting these contaminated soils. So the last picture is this leachate that I collected. And then we'll pass that leachate through these filters, these cartridges. So these are called solid phase extraction cartridges. What you do is you pass all of your leachate through, and the PFAS get stuck onto that little white puck. And then you can extract the PFAS that are on that puck using methanol. Then you can put it onto our instrument, which is an LC-MS-MS. And then we get our beautiful data.
And
so,
then just real quick, so that instrument's over in John
yes.
Bowden's lab.
So, yeah, that's where Dr. Bowden comes in, and he has all those instruments. And we've been trained, to use them and analyze our PFAS samples there. So what we see, so first off, just looking at the total concentration of these soils. So right off the bat, soil A is kind of our high concentrated soil. It has around 2 micrograms per kilogram of PFOA and 500 micrograms per kilogram of PFOS. And this is above the regional screening levels that the EPA has for PFOA and PFOS based on leachability. And then it's also above those provisional soil cleanup target levels for PFOA and PFOS. And those are listed at the bottom of the screen. So then we also have our soil B, which is kind of our low concentration soil. And it's above, or it's below the provisional soil cleanup target levels based on leachability, but it's still above the regional screening level for PFOS. So now, kind of to refresh everyone of what the leaching data is going to look like compared to that equation that EPA uses or FDEP uses. So if the data falls above the estimated line, then it's the equation is underestimating the amount of leachate that's going to come off. So the concentration is higher than your estimated amount. That's an underestimate. If it's below, then your estimated concentration is overestimating the value. So this is what we see. So for PFOA in our soil A, it looks like the EPA regional screening level equation tracks fairly nicely with the concentration that we see leaching at the different liquid solid ratios. And then we see kind of the same thing for our low concentration soil. So for PFOA, it looks like the EPA values track better than the FDEP ones. Then we go into PFOS, and we kind of see sort of a different story for our high concentration soil. The values are much lower than what the EPA RSL would have predicted. So this means that the EPA regional screening level equation is actually over predicting, the estimated amount of leachate that you would expect to come off of these soils at these different liquid solid ratios. But for the soil B, that low concentration soil, it's actually the opposite. It's well above both FDEP and EPA equation. So in soil B, we're seeing that both equations way underestimate the amount of leaching that we see.
So just Jake, one thing real quick, you keep
Mhm.
referring to the EPA equation and the DEP
sorry.
equation. They're
Yeah.
really the same equation.
Yeah,
It's just
yeah.
the assumption of the partition coefficient.
I misspoke. Yeah,
Going
it's more the values that go into these equations. Sorry, not the equation themselves. They're both based on the same equation. It's just the values that are chosen for partitioning, as Dr. Townsend pointed out. So the fact that you see different soils leaching at levels, higher than you would expect and lower than you expect means that there's probably other factors at play that these equations aren't accounting for. So now I'm going to move on to some of the compounds that are only included in the regional screening levels. So this is PFNA, PFHXS, and PFBS. So first, for PFNA, in our higher concentrated soil, the leaching values fall pretty well below our expected leaching. So it's over predicting the amount of leaching. But for our low concentrated soil, it's tracking pretty much spot on with the EPA equation. And then kind of a similar story with PFHXS, just slightly below the expected value, but it's tracking very well with the EPA. It's fairly similar with the soil will be the low concentration, except for the really low liquid solid ratio. You see a deviation from the expected leachate.
Did Jake freeze for anyone else but me?
Mhm. Yeah. Oh,
Yes, he did for just a minute.
Yeah, you were.
you want me to go back? Okay, sorry. There's some. Okay, so I'll just go back to explaining this slide. So for PFHXS, we see kind of a similar thing where the leaching data tracks pretty well with the values used for the RSLs, or it falls slightly below. And then for soil B, which is our low concentration soil, we see that it's tracking better at higher liquid solid ratios, but then there's some deviation at the lower liquid solid ratios. So then for our last compound, which is PFBS, so we didn't find this in our low concentration soil. This is only in the high concentration soil. We see, again, the EPA regional screening level values are tracking fairly well. It's only deviating slightly at the lower levels, and then there's some higher deviation at lower liquid solid ratios. So kind of what is this?
Abbott had his hand up.
I'm curious if you could go back.
Yeah.
So these numbers on all the slides so far,
Yeah,
they are all detectable, right? So we're not looking at concentrations that are below detection.
yes, yes.
Okay. Thank you.
Mm-hmm. So kind of to wrap up, what all of this really means. So obviously, the regional screening levels, they have much lower values selected. So you'd expect them to be more conservative than the provisional soil claim target levels. And the reason that you see this being more conservative is kind of these partitioning coefficients that they assume in these equations. So on the right-hand side, I have the FDEP values, and on the left, I have EPA. So you can see that they are definitely different from each other, and this really is what's accounting for this deviation in this expected leachability. And we also kind of see that for certain compounds, especially for PFOS, there's more factors at play that we're controlling leachability than what actually goes into the equations. So if I go back, you see that for one of the soils, the equations, the EPA equation underestimates it and it tracks fairly well with the FDEP equation. But then for another soil, so it'll be the leaching data was much higher than what both equations expected to come out of it. So this just implies that there's other things going on, that these equations aren't accounting for. And then finally, it seems that for PFOA, PFNA, PFHXS, and PFBS, the RSL values do track fairly well. There is only, slight deviation at, the higher or the lower liquid solid ratios. So overall, I would say that the EPA selected values better fit expected leachability than the FDEP values.
Maybe we could stop for a second and
Yeah.
see, and obviously, this is an issue for, that Brian and his group, and this is the first time you've seen it, so I'm not expecting you to have a lot to say. Obviously, you need time to review it. The kind of big picture is that we set out to see whether or not using soil cleanup target levels based on the leachability risk threshold or protection of groundwater, whether those were protective compared to if you were looking at just a leach test. And I think what overall it finds is that while it's not universal, for the most part, probably you could say that the DEP assumed values or calculated values are probably tended to be less protective than what the EPA values would be, which is, that makes sense. But the idea is that you're probably underestimating the amount of leaching associated with the PFAS based on the currently assumed KD values that are being used, and the ones that are being reflected in this newer set of data for the RSLs that EPA has look to be overall, not universally, look to be a little closer fit. So I don't know, that's kind of a lot to throw at you, but any questions on that, or you want us to go back to any of the slides? Oh, yeah, Helena.
Yeah, no, this was really interesting. So it seems like it all boils down to the organic carbon content of the soil then? Is that what it boils down to?
Well, so the organic content, in the way it for the way it works is the KD is the KOC times the fraction of organic matter. And so the idea is that if you plug in the organic matter content for your soil, and then the KOC value, you can get the KD value. But it goes beyond that, meaning that it's the partition coefficient, which is a function of the organic matter, but which one of those you choose, because you could have the same organic matter content for both sets. It's just what KOC you end up picking, which results in the particular KD that you got. So in theory, if you have the right KOC value, then it should do a good job at any organic matter content, assuming that that type of isotherm holds up.
Okay, yeah, because I'm trying to remember the KD is KOC and the organic matter.
Correct.
But then the KOC is a function of the octanol water partition coefficient, which would it's a function of the chemical. It's not so you wouldn't be able to choose. The thing that really varies in the field would be the organic carbon content.
Yes.
Yeah, but they choose. I mean, the way these are developed is they pick an octanol water coefficient for these chemicals. They've determined those for the different PFAS species, and that's what goes into the calculation. So you as a risk assessor could go measure your organic content, and you could come up with a site-specific target level based on leaching. But if the assumptions that went into it for that chemical were wrong, then it could be overprotective, it could be underprotective. And what this data hopefully allows us to do is to say, well, actually the KOC or the KD for this particular assumption works pretty well based on these soils and for these chemicals, but for others, maybe not. And so that's what ultimately will come out of this.
Okay, so different agencies are picking different octanol water partition coefficients to run the analysis as well. So there's differences in organic content, and there's also differences in the octanol water partition coefficient.
Yeah, because you can enter and then you enter the organic matter into the equation. So that's something that we can control. We can measure it. We can put it in there. But it's the assumption of the KOC or the KOW that ultimately is going to be what dictates whether it's good or bad. And so where we're at is in the state of science right now, there's just not enough info, and it's evolving. But Leah, please jump in.
Yeah, so I just wanted to clarify a little bit, because when these were developed, when the FDP numbers were developed, they were developed back in actually 2018, the end of 2018. At the time, the US EPA did not really understand the octanol water partition coefficient. Now we have a better understanding. It's more like a detergent. You can't really estimate it. So what I did was put it in the EpiWin program, which looks at the structure and tries to estimate what that partitioning coefficient is, with full acknowledgement that that's a computer estimation of what it was going to be, but it was the best that we had at the time that was being put out. So with the new documents, EPA has gone back, and there are some published data now on what those KDs should be. So it makes sense to me that EPA tracks a little better because they're actually using published KDs versus my use of like this estimated computer. What would the KD be for this structure?
Good, good, thank you. Any other questions, Thabit?
Okay, so is there more data you guys are presenting?
It'll be a different project.
Okay, I'm curious what you cannot. Oh, I don't want to share my screen. I'm curious. Let's go back a little bit. So let's talk about your extraction.
Yeah.
So you did. Yeah, it doesn't matter. Let's leave it there. Let's take a look at a graph.
Okay.
Your extraction, walk me through it. You put your material, soil, in the 2 liter or HDPE.
Yeah.
And then with head space, and you tumbled it for what, 18 hours?
Yeah, 18 hours.
Well, it
Now,
depends. 13, 16.
Oh, it's 24, I think, actually.
Yeah, it's just following standard EPA 13, 16.
So it is. I don't know whether the 18 hours is accurate or not. We're talking about organics. We're talking about organics that potentially are well sorbed onto the surface of soil. So could the differences be that we didn't extract for long enough duration?
It's a good question. Again, we're using the EPA methodology. There is no differentiation between organics and inorganics for in that leaf method.
Well, I understand they're trying to develop for PFAS at the moment, but I would suggest taking a look at the extraction, see if we doing it for a little bit longer duration. That's at least 1 liquid solid ratio may be warranted. I know it is more samples.
I agree. I think something that's interesting that as you approach this liquid solid ratio of 10, back calculating out the mass that released, it starts to approach the totals. So I think you are leaching, a very significant fraction. I don't think if you increase the leaching time that you would see like a huge jump in your concentration of PFAS. I think you would see more, obviously, because you're increasing exposure to your contaminated media, but I don't think it would be super dramatic.
Well, I don't know if it's a given that you would see more. I mean, maybe.
Right, it is not.
Yeah.
I was curious. We have the data on ash and liquid solid ratio is at least for the 2 compounds, PFOS and PFOA. Have you looked at that data? It would have been helpful to potentially.
I mean, that's a good idea. That wasn't part of this evaluation, but
Okay. Thank you.
All right. So what I would suggest, is just in the interest of time, is that we're going to ask everybody or give everybody the opportunity to review the report and have further conversations. But we've got one more topic. It'll take a little less time related to this, and this is the idea of if Jim Clark, for example, were to receive a bunch of contaminated liquid and he needed to bulk it up before going to a Class 1 landfill in the state of Florida, does the PFAS simply stay in the bulking agent, or will it all leach out? And so we've done some testing to try to answer that. So Jake, why don't you take it away?
Yeah. So as Dr. Townsend mentioned, bulking of liquid waste is something that is commonly done. So because PFAS are not listed as a hazardous waste, they can be disposed of in a traditional landfill. And many PFAS containing waste are liquids, you know, AFFF, remediation wastewaters, etc. But by default, liquids actually can't be disposed of directly into a landfill under 40 CFR. So a common strategy that's done is that you would add an absorbent material, which is called, you know, a stabilization or a bulking agent to your liquid until they don't contain any free liquids. So this is kind of an example of what this looks like at the larger scale. So how you actually, you know, determine, you know, if you can actually dispose of this liquid waste into a landfill is you have to pass something called the paint filter test. So what you're doing is you're taking your liquid, you're mixing it with your solid or bulking agent, and then you would put it in this paint filter in a funnel, and you would see, you know, does any liquid actually seep out of it over a given amount of time. And if no liquid does, then you pass your paint filter test. And what's commonly done in the industry is that you would use different bulking agents. So, you know, if you have AFFF, you could use, you know, clay or sawdust or cement, whatever is cheap and available. That's typically what is done. So our question was, you know, do these different bulking agents have an effect on the retention of PFAS? So to do this, we got two PFAS containing liquids. One is an AFFF solution and one is a PFAS containing wastewater. And then we used 4 different bulking agents to bulk up these liquid waste. We got bentonite clay, biochar, sawdust, and cement. And then we ran EPA method 1311, which is TCLP. This is meant to simulate landfill exposure to a waste over time and evaluate what would leach out into landfill leachate. So the idea is we put a known mass of PFAS into our bulking agent through AFFF, and then we take that mixture, that bulked mixture up, and we put it with our TCLP solution, which is meant to simulate landfill leachate. It's at a given pH, so you can kind of think of that as years of landfill exposure. And then we take this extraction fluid at the end, and we see the mass of PFAS that transferred from our bulked waste to the actual extraction fluid. So this would kind of simulate what would the mass of PFAS be in landfill leachate over time. So in real life, this is kind of what the experimental workflow looked like. First, we bulked our liquids with different bulking agents. Then we ran our leaching tests. Then we do the same thing we did with the previous leachate. We put it through, you know, the cartridges and analyze it on our LCMS-MS. So just jumping right into the results. What we did is we had a AFFF solution and a contaminated wastewater. So for the AFFF, this is what it looked like. This is a new age AFFF. So it's kind of marketed as a replacement for old AFFFs that contained PFOS and high concentrations of PFOA. So you'll see that it's primarily shorter chain species with a lot of precursors, and predominantly it's 90% this one precursor that's listed at the end here. This is what the AFFF solution looks like. It's this thin yellow substance. And what we did after we bulked and did our leaching test, we found the mass of PFAS that was actually retained by each bulking agent. So quickly, I'll just kind of explain what one of these means for a compound. So for PFOA, you would see that for the bentonite clay, only 41% of the mass of PFAS that we actually put into, or PFOA, we actually put into the bentonite solution was retained. So about 60% ended up coming out into the leachate, while for, you know, our biochar, we see almost 99% retention. So we're seeing that different bulking agents do have an effect on the retention of different PFAS species. So this is another way to look at it. just blown up for every single compound that we found in that AFFF solution. And this kind of tells a slightly different story. So the total mass of PFAS was really dominated by this last compound. So, you know, your total retention is really impacted by how well the bulking agent retained the NCMAP PFAS. But another thing that we found that was pretty interesting is that—
Talk about colors, Jake.
Yeah, okay. So the green means you retained a large majority of your total PFAS. Orange and yellow is you didn't retain that much to none at all. And then red means that we're seeing more PFAS there than we actually put in. And we don't believe this is a mistake on our analytical side, but we think that that some precursor species are able to transform into these short chains. So research has been done, and this topic is talked about a lot for like biodegradation of larger precursor species. But basically, there's larger PFAS that can transform into these short chain terminal species given certain conditions. And because we see it in the cement, it's possible that, you know, these alkaline conditions that are in cement dust creates, you know, more of these short chain species than what we actually put in. So there's this transformation going on.
Well, just to hop on, I mean, look at the 46% for cement for that precursor at the bottom, right?
Mm-hmm.
And so you can see that a lot of it wasn't retained, but there's more of it produced of these what, short chain or these terminal species.
Yeah.
So there's literature that shows high calcium, kind of calcium oxide environments will do some transformation of the precursors to terminals. And so it looks like the cement is actually transforming some of that primary precursor species, which is found in that particular AFFF blend into some of the shorter chain terminal species.
Mm-hmm. So moving on, we also looked at another liquid. This was our impacted wastewater. So just looking at the characterization of this wastewater, the total concentration of PFAS is much lower. This is what you'd expect. You know, it's diluted with groundwater or rainwater. And it's mostly terminal species. So, you know, with the wastewater, it's been given time in the environment, maybe a lot of these precursors have broken down. So it's a majority of these precursor species. So then when we look at how this actually compares to the AFFF bulking, we see that all of the roadmap chemicals were retained, no matter what the bulking agent is. So this suggests that at really low initial concentrations of contaminated liquid, that you can basically sorb all of your PFAS to that solid. It doesn't matter what bulking agent you use, because there's so much available surface area compared to the concentration of PFAS that you actually have. So again, breaking it down to this large table view, we see kind of an interesting trend again, where there's less retention of these short chains. Maybe there's some more transformation going on, but we see that in general, most of the PFAS, the terminal or the EPA roadmap compounds were retained. So kind of just to sum up everything from this experiment, certain bulking agents were better at retaining specific PFAS species. Generally, the larger chain species tended to sorb better. This makes sense, given there's literature that suggests that large chain species do want to sorb to solid material rather than be in aqueous phase. And then for low concentration wastewater, we saw that 99% of the mass of EPA roadmap PFAS were retained. So it suggests, like with your low concentration, you can use any bulking agent and you would expect to retain those PFAS. But for the AFFF solution, the higher organic matter bulking agents like the biochar and sawdust were the ones that performed the best at retaining those roadmap chemicals.
So this, I was kind of surprised at these results. I mean, the thought is if you bulk your PFAS up, you put it in the landfill, that you're still going to eventually see the PFAS come out. I wasn't expecting it to be retained. Now, it's only retained in this TCLP. That doesn't mean that in the landfill under pressure, if water is squeezed out, that it won't still be part of the landfill environment, but it relates to other stuff that our entire research team is working on. Like we're getting ready to build some simulated, or not build, they're already built, but to test these simulated landfills that will have PFAS as part of the waste. So one question is what fraction is actually sorbed or attenuated onto the organic matter in the solid waste itself. And Helena, one of her students, is working on a mass balance of PFAS in a landfill. And so the question of how much of that is actually retained in the landfill, it was just a little bit surprising that as much of it was. So Jim, I would have predicted that if you were to bulk a bunch of liquid PFAS waste up, that probably you'd be certainly legally allowed to put it in a Subtitle D landfill. But I would have thought more of it would have probably been leachable. So it looks like for these high organic matter chemicals, which goes back to that point Helena brought up before about the organic matter playing such a big role in terms of sorption, it appears that a fair amount is retained. Now, that doesn't mean that that's going to impact your PFAS concentrations and your leachate tremendously, but it does suggest that a fair amount of the stuff that's bulked up will remain. Anyway, I don't know if anyone else was surprised by that or if has any questions on that. David.
Yeah.
I'm sorry, I don't want to continue hogging the airtime here. My concern is not about, I mean, while I was surprised by the retention, let's go back a little bit. Go back go back. Yeah, stop here, wait, move forward. Right here, you're seeing a more than 100% increase in a couple of compounds concentration. And that is attributed to conversion of short chain to longer chain. That conversion, in my mind, should be concentration independent. So it doesn't matter how much concentration you have. Now let us move forward to the water.
I didn't understand the point of the concept.
That's mean the conversion is going to happen whether you have 10 microgram per liter or 100 microgram per liter. You're going to convert some precursors to terminal species because of the calcium, because of whatever is in the cement, right?
But just remember, both solutions didn't have the same chemicals in them, and so this one had a lot more of one particular precursor that was not in the other one.
True, but okay. I mean, but you would expect to see transformation on the same on par when you're looking at your contaminated water sample. And what I was surprised with, there some of them not even close. If you move forward a couple of slides to that, I mean,
what are you surprised by?
You see the first they're 15%, 86, and that is, you're not even recovering what you started out with, right? For PFBA under cement, there's 15% recovery.
That means that there's 15% of the mass is retained, so that 85% of the mass is there, which means it could be because it simply wasn't sorbed or it was produced in the reaction from a larger.
Anyway, I need to sit and think more about it.
But I think your point was a good one, Thabit, is that, you know, it's great to present this, but you got to do the mass balance kind of truth check to make sure that things add up like you would expect them to add up. And I'd be lying to say we've done that to the level we need to yet. Elena?
Also, just to make sure I understand, because I see negative values here. So there's conversion, I presume that's occurring, and that's why for biochar, the PFBA is negative. So there's conversion.
So the negative value means that we saw more mass going in than what comes out. So 0% would mean that all of the mass we put in would come out. Negative means that we saw more come out than we put in. And then 100% means that we didn't see any come out compared to what we put in.
So something was converting into that so the biochar is causing some reaction to occur.
Yeah, That's
I apologize if you went over this. I missed a few minutes, but did you leached these materials by themselves? So for here, you've already subtracted out any.
yes. So I
Okay.
subtracted background concentrations. Yeah.
That's a good point, because one thing we've seen in some of our other work is depending on the source of biochar, there's actually some PFAS in biochar, depending on the source of the wood or the organic matter that was used to make the biochar.
Yep.
So then we're over past 11. Why don't you just move on to the last slide? Jake, one more, or are we done there?
I think this is it.
Just stop sharing.
Yeah.
So where we're at then is that we have a, that's kind of our set of data for 2 different research topics. The idea is now that we have a draft report that is not quite done, but almost done. And then at some point, then it'll need to go out to Helena and John and the rest of our team to kind of go through its review. But then what we would like is we would like to send this to members of the TAG for them to review. And I know that was a lot of information that we presented to you pretty quickly, but the idea is that if you could take your time and share comments on the ultimate report, then it would be very much appreciated. Any other questions? I apologize. We went over, I think, our allotted hour. John, share. You have any last words of wisdom?
Can figure out how to unmute.
Well, Jim Clark, you're muted up, Jim. Or Kim, please.
I just was going to thank you for the interesting, thoughtful presentation.
Thank you.
Thank you for coming.
Jim, did you want to say something? You're muted again now, so you need to unmute. Can't hear you, Jim.
Yeah, we didn't hear that. Sorry, Jim. The unmute.
How about now?
Yep.
You guys did a hell of a job putting all that together, and I just want to thank you for that information.
Sure.
Thank you for coming.
Dr. Tolomat, since you monopolized all the time, do you want to continue and ask some more stuff?
Yeah, I mean, I was gonna wait to ask you questions later, but I would take also a look for the conversion. I would take a look at the temperature. When you're adding liquid to cement, isn't there a heat generation at some point?
Yes. That's correct. That could play a role in that conversion.
Good point.
One thing though, it's not like that wouldn't happen at full scale either. So we're still like collecting information about what would happen when you did this, even if the mechanism is heat or calcium.
I mean, the challenge for a regulatory body is taking a look at the data, depending on where you collect your sample and how you preserve it, and analyze it, you get different results.
All right, if nothing else, what we'll plan on doing is at some point the TAG will get a copy of the report. We'll ask you to give some feedback on it, and then we'll finalize everything. And then for John and Helena, we're probably still, I don't know, maybe a week away from giving it to you, depending on how much energy Jake still has to. Now that we've gone through this process, I think it should be good to pretty much wrap it up, at least to that point. Okay. All right. Thanks for everybody coming and participating.
Thank you.
Thank you.
Very
Thank you.
interesting.